hair look a mess? Because I just did my science workout plan. Check it out. So anyway, I'm trying this Google form, y'all. I am not going to give up because it seems more simple and compact because I'm getting like 45 messages a day about I don't know how to attach a file. I don't know. Am I moving in slow motion? I don't know how to play the video. So I feel like if everything's in that Google form, it'll be easier. So I'm going to take this lesson. I'm going to upload it to YouTube, put it in a form. So everything's just in one section for you. I just want to have this ready to go. I do want to go over, my battery about to die. Hold on. Press pause. My bad. Had to switch rooms when battery died. So, we're closing out evolutionary history and how speciation occurs, how traits change in descendants over time as they move further and further away from the ancestor population towards present time. So when we look at this evolutionary tree, we know now that when one population is divided into two new environments, the two populations might change and become different over time, similar to this evolutionary tree below. Imagine that each of the new descendant species was split again into two new environments, and even more time went by. Now there are 4 new environments. Use the tree below to think about the differences between those 4 new populations over millions of years, and answer the questions below. Which group of descendant species is most likely to have body structures that are the most different from the ancestor population? So would it be descendant species 1 and 2, or would it be A, B, C, and D? We can look and see that the furthest away would clearly be A, B, C, and D. Where did we leave off, children? Okay, so which descendant species is most likely to have body structures that are the most different from species B? Would it be descendant species 1? They seem relatively close. Descendant species C or descendant species A? Well, as we can see, descendant species 1 and A are directly connected to B, so it would definitely be descendant species C. Ooh, okay, there we go. Descendant species C. Does everyone see that? Cool, I'm going to keep going. Key concepts. Among any 3 descendants, the 2 species that share the most traits are the most closely related to each other. The 2 species that share the most traits are the most closely related to each other. So we're going to go down to reading embryos. You have this and a question with it in your Google form. I'm going to read it out loud for anybody that needs me to. Comparing embryos, evidence for common ancestors. If you saw an animal before it was born, would you be able to tell what kind of animal it was? Maybe not. Many animals that aren't similar at all when they're fully developed are very similar when they're still developing. Unborn animals that are still in the early stages of development are called embryos. So there we got the definition of embryos. People have been studying embryos to understand animal development for more than 2,000 years. The similarities between animal embryos have also helped paleontologists understand how animal species have changed over time through the processes involved in evolution. A fully developed chicken looks very different from a fully developed fish, salamander, or tortoise. However, as you can see in the picture, the early stages of embryos for these 4 types of animals are very similar. Let's circle that. They have the same basic shape and many of the same parts, including parts they won't have when they grow up. For example, both fish embryos and chicken embryos have parts called gill slits at a certain stage of a development. However, only the fish actually grow gills to allow them to breathe. In chickens, the gill slits go away and lungs develop instead. As animals grow, they develop features that make them different from one another. The similarity of different types of embryos is evidence that many species that are very different today share common ancestors from the past. Comparing embryos shows us that organisms of different species can be very similar in the early stages of development, even if the fully developed versions of the species are very different. This is the question you would have to ask online. So now let's look at this evolutionary tree. Part 1, Create species A, F, and G by using body structures that each species probably had. Look at the descendants and or common ancestors of each missing species to figure out the likely body structures. Hint, there is more than one possible way to build species F and G. Your teacher will project a color version. We can't project, but it's okay. Let's just go down and answer these questions. So only species H and I have this structure. So when I look at H and I, they both have the gray background and they both have this snow-like structure with another connecting snow-like structure. These are the only two on the board that have two of those structures connected with a bar, okay? Only species J and K have this structure. Okay, they have the dark background and they also have like this little bolt here. Okay, got it, cool. Let's go down. Species H, I, J, and K all have this structure. So let's see, H, I, J, and K. All of them have that basic like snowflake looking structure. Screw or snowflake looking structure. Because we can't really tell if it's a screw in black and white. But as we can see across the board, they all have some type of common trait, similar to all those embryos having some type of common trait, which we know means that there is a common ancestor. So we will think, what might F look like, right? So maybe for here, F might have a snowflake. It is not a snowflake, but that's what we're going to call it. A snowflake with another one attached, like I, which has caused this branch of H and I. And then G could possibly have a bolt, like one side of the snowflake with a bolt at the end, which caused K and J to be descendants. Okay? So that's just really what it's a matter of doing for like speciation and evolution. We're literally looking and comparing traits. That's how you can determine if there's common ancestry. Moving on down. So which species I, J, or K is the closest relative to species H? What is your evidence? So which one would we think, guys? Obviously, it would be I, right? Same background, same type of connection piece. Now, which species H, I, or K is the closest relative to species J? What is your evidence? Okay, so when we look here, it would definitely be K. They almost look identical. Same color background, okay? This is also a part of your Google form. So I won't go over that because I want to see if you understand it. Stamping understanding. Species have the most similarities and shared traits, which species they are more closely related to. Species have the most similarities and shared traits, with species they are more closely related to. Okay? Independent practice, I did not choose all of these, but I chose 4 that I really feel like will stamp your understanding of how shared traits and similar traits bases off of common ancestry, okay? And then we'll save some other ones for tomorrow. So all you have to do is complete your Google form. That's your work for tomorrow. Got it? Cool. Everybody have a wonderful day.